I would like kindly to remind our participants that this webinar is being live cast and being recorded. So kindly be courteous and objective, and of course not offensive. Thank you. Welcome, everyone. Thank you. Thank you for joining the 6th Nile Basin Development Forum. Today is the last session under the theme Adaptation to Climate Change. And today, our last session, it is about drought monitoring and forecasting over the Nile Basin. I would like to start first again with some housekeeping. Please type your name, affiliation, and country of residence in the chat room area so that other participants can know who's present. For our speakers, please mute your mic, turn off your camera, except when you are speaking. Please use the chat room to share and exchange ideas. You can also post questions in Q&A feature. Finally, I would like kindly to remind our participants that this webinar is being live cast, being recorded. Please be courteous and objective, and of course, not offensive. Thank you very much. Okay. Now, on behalf of the Executive Director of the Nile Basin Initiative Secretariat, I would like to open this session. The Nile Basin Initiative, in collaboration with the government of Ethiopia, is organizing a series of webinars in the 6th Nile Basin Development Forum under the theme Rethinking Regional Investment in the Nile Basin. The Science Policy Practice Dialogue is organized to bring together NBI with its stakeholders from the Nile Basin countries and also around the world. The goal of the 6th Nile Basin Development Forum is to enhance transformation processes in projects that will contribute to the Nile Basin Initiative shared vision, which is to achieve sustainable socioeconomic development through the equitable utilization of and benefit from the common Nile Basin water resources. We have different themes under this Nile Basin Development Forum. We have water resources management, we have environmental and wetlands, we have water food nexus, also adaptation to climate change, and finally transboundary water governance. We started on the 9th of March and we will continue up to 29th of April. The Nile Basin is one of the most critical transboundary water basins in Africa, with the River Nile playing a crucial role and resource for most of the economic and social activities for the countries in the Eastern and Northeastern Africa. The adverse effect of climate change, which is expected to worsen in future, should little or no effort be done to avoid the current trends. The climate is changing, putting a range of natural and human systems at risk and promoting communities, governments, and organizations to step up their efforts to adapt. The Nile Basin Initiative developed a drought monitoring and forecasting tool for the entire Nile Basin. So welcome everyone to this webinar. Let us have a fruitful presentations and discussion, and let us work together to incorporate these findings in our decision making for River Basin agenda. Thank you very much. Allow me now to share with you the keynote presentation for today's session. Yes, thank you very much. Okay, my presentation, it is about the work that we did related to this topic or related to this session of today. And it is about drought monitoring and forecasting tool for the Nile Basin. This is the outline, introduction, drought monitoring and forecasting. I will take you also quickly through our bulletin that we started to make every 2 weeks. And also I will take you quickly also through our online webpage. So this activity, it was under goal 5 of the Nile Basin 10-year strategy. The NileSec intends to develop a short-term to seasonal river flow forecasting, and in that project or in that activity, in the 7th component, we were about to develop also a drought monitoring and forecasting tool and bulletin. The drought monitoring and forecasting are operational now, and this means that historical as well as near real-time data is being automatically updated for the Nile Basin on a regular basis every 3 to 4 days. In our bi-weekly bulletin, the most relevant data set and indicators to monitor and forecast the impact of drought are the following. We have 3 important sections. We have meteorological drought, we focused on that, and also on the agricultural drought, and also in the hydrological drought. One of the examples in the meteorological drought is this standard precipitation index from GPM and also from NOAA. We also have under the agricultural drought, the NDVI, which based on MODIS NDVI dataset. We also have soil moisture content under the hydrological drought. This is just an example of our web page. These are small catchment, and we have also the 10 large sub-basins of the Nile Basin. And you can generate even yourself different kind of information from this web page. Anyone can join that page and can register in that page. Either you are from the Nile Basin countries or even out of the Nile Basin countries. You can generate different time series. You can area average over different sub-basins, and you can use different indices, around 152 variables and indices. You can use them. You can generate different kind of information. You can even download the image and the generated graph. Is the front page of our drought monitoring and forecasting bulletin. We share it every month with all our stakeholders, like around 2,400 stakeholders. We did, and we developed this activity in collaboration with our partner at Intro. They supported this activity. We also disseminated this information through our integrated knowledge portal through the IKP. You can access this information. You can also access also this information in this link, and then you can go to the drought monitoring and forecasting. These are some important and useful links. You can use them to test, to manipulate, and to generate different kind of results. Allow me to go quickly to show you just our bulletin, what is there. Yes, so yes, we generate, like as I indicated, long term of rainfall. This is like a forecasted rainfall. We generated this kind of information. Here, if you see this map also, it is for rainfall deviation. And here, if the deviation is below 0, it is in this red color. This map also for the 3 months SPI, the Standard Precipitation Index. It is available or we generate it bi-weekly, this bulletin, but we share it with our stakeholder every month. But if you are interested to get it also bi-weekly, you are welcome. You can contact us here at NileSec. This is also the seasonal rainfall forecast as an ensemble forecast in our bulletin. These are the forecast also in different sub-basin, like for example here, this is on the White Nile, this is for the Blue Nile, this is for Takazi Adbara. We also, as I indicated, we generate the soil moisture status and this soil water index. And this is the map for that. This is also a map for the root zone storage, if you are interested on that. Yes, these are also other type of maps for different sub-basins for the same thing, for the root zone storage, deviation. Yes, and this is the map for the NDVI. Allow me to take you also quickly through our web page. You can go here, you can select from these 152 indices and parameters and variables, you can select from them. Like for example, here, this is chirps. We have historical ensemble, monthly mean, different kind of indices. Like here, this is SPI for 1 month. This is the SPI for 3 months. So you can select whatever you want. And then here, you can easily generate a time series if you are interested on a specific, for example, sub-basin. These are the large sub-basin, but you can even like zoom in and select a small sub-basin. You can generate like different kind of graphs and you can download them. So there are like a lot of opportunities in this free web page for Drought. Please explore it. We cannot now go through all the features of this web page, but this is just to let you know that you can do the same and you can explore different things here. And you are welcome also to contact us if you have any question. The report, it is here. Here, this is the data. This is the report. You can download the report that I just showed you. At any time, you can come here and you can download the report. Yeah, so this is just briefly to tell you about the services we are doing here at the NBI, at the Nile Basin Initiative Secretariat. But also we have other experience from Intro. They have also very nice and interesting drought monitoring and forecasting tools. You will see that later. Thank you very much. Thank you. Now let us start the second part of this session. It is about presentations from our experts. The first presentation, it will be by Justin from the Princeton Climate Analytics. His presentation is about drought forecasting in the Eastern Nile. Dear Justin, please kindly introduce yourself, and the floor is yours. You are welcome.
Thanks very much, and good morning or good afternoon, everybody. Let me just see if I can turn all this on. So I'm going to talk about drought forecasting in the Eastern Nile Basin. It follows on nicely from Motadir's previous presentation, and I'll show you some complementary activities that we've been doing in collaboration with Intro. And this is work that has been done through Princeton Climate Institute and also my home institution, University of Southampton in the UK. So the objectives of this work has been to develop drought early warning capability, recognizing that that is a key element of any initiative where you're thinking about providing information, early warning information to try to mitigate the effects, the impacts of drought. So our overall objective has been to develop a seasonal hydrological forecasting system for the Eastern Nile Basin. So the emphasis here on hydrological forecasting, as you know, there are plenty of initiatives and data sets and products that provide meteorological data, so precipitation, temperature, but the key here really is to get down into those key hydrological variables where we essentially feel the impacts of drought. So the sub-objectives here have been are listed down below here. Firstly, to identify the best approaches for forecasting. So there's lots of options there in terms of, say, statistical or dynamical. Dynamical is often the best way to do this through seasonal climate forecasts using climate models. But there are many approaches there and many different sources of information, different models. Then coupling those climate forecasts to a hydrological model so we can actually produce those hydrological forecasts. Then evaluation across a range of metrics. So drought comes in many flavors and different forms. So depending on your application, depending on the impact that you're interested in, you may be looking at a bunch of different metrics associated with drought. And then the idea was to demonstrate this operationally with forecasts out to 6 months. That's generally what seasonal climate forecast models are producing. And then finally, to deliver the system through an online interface and with capacity building training in using that system as well. So here's an overview of the system. And as you can see, it's made up of several components that are coupled together. At the center of this is a hydrological model. That hydrological model is being run operationally in near real time, about a day or two behind real time. And that is forced in real time by different precipitation and meteorological data sets. We mostly use the MS-WEP gridded data set, which is a merging of satellite data, reanalysis model data, and on-the-ground station data as well. And that also provides a historic simulation that goes back to 1979 that provides the climatology and an assessment of historic risk as well to put the current conditions and forecast conditions into context. So that is updated every day. And once a month, we provide a seasonal forecast that takes data from the European Copernicus Climate Change Service. So there are a suite of climate models there available that I'll talk about in a moment. So that provides precipitation and temperature that we downscale and bias correct. And then that is put through the hydrological model. That's complemented by other satellite data which were mentioned before actually by Motadir, in terms of information from MODIS and SMAP and so on. And then from that, we obtain monitoring and forecasting data. So the monitoring data is updated every day, as I said, about a day or two behind real time. And that provides us with the precipitation, the hydrological variables, including stream flow, soil moisture, and a whole range of different drought indices that were also mentioned before. And that's available through the online interface, which I'll talk about in a moment. So in terms of the climate forecast, we did quite a bit of work trying to analyze the available climate models that are within the Climate Change Service, the Copernicus Climate Change Service, and you can see them listed here, which include the ECMWF model, the UK Meteorological Office model, UKMO, and models from Meteo France, the German Weather Service, and CMCC in Italy as well. And you can see the attributes of those different models in terms of their forecast length, the number, how often they produce the forecasts, the number of ensemble members, and also the hindcast period, which is really important. That hindcast period allows us to do evaluations of the skill of these different models and then make determinations about how we're going to use them. You can also see the spatial resolution as well. So I'll show you some evaluations of these models, focusing mostly on the ECMWF model, which turned out to be the better model in general across the region, and that's true across Africa as well. So here's some a brief summary of some of those evaluations, focusing on precipitation, and as I said, focusing on the ECMWF model. Along the top here, you can see maps that show the correlation between the forecasts at different lead times. So these are monthly lead times, so lead 1 month, 2 months, 3 months, and so on. The correlation of those forecasts with our observational data, which in this case is the MSWEP gridded precipitation data. And so the darker blue colors indicate higher correlation, getting quite high in fact. And you can see that in the southern part of the basin, the wetter part of the basin, and quite low in the drier part of the basin. And that's essentially showing that the forecast models are following the seasonal cycle. That's where you get quite high correlations there. More importantly, if you look at the anomalies down below, so this is removing the seasonal cycle. So this is testing the skill of this particular model in terms of how it picks up the anomalies from month to month relative to the long-term seasonal climatology. And you can see that the skill drops quite rapidly. And you see it coming down to a maximum about 0.5, 0.6, 0.7 in some places. And you can see that as we go out to lead 2, lead 3, then the skill drops off quite quickly. So much of the skill, where there is really in the first month, as we might expect, because of the chaotic nature of the weather. We've also done evaluations by season. So that previous slide was showing evaluations over all months at the kind of point scale across the basin. So here's a few examples where we've looked at the skill averaged over larger regions. In this case, this is for the whole Eastern Nile. You can see one example here of precipitation at lead 1 month, and you can see that versus the observation that the MSWEP data. And you can see at lead 1, you can see it picking up these anomalies from month to month, from year to year across the hindcast period. And we've broken that down over on the right here in terms of the different seasons. So the black line shows the correlation at lead 1 down to lead 6 for all months aggregated together. And then we see it for the different seasons as well. And what you see is the skill is a bit higher for the drier seasons and a bit lower for the wetter seasons. We would actually like to see that the other way around in some cases, to have better skill of when it's going to be wetter in those kind of wetter parts of the basin. And I haven't shown anything for the temperature here in these slides, but the skill for temperature is a little bit better, and it actually captures the overall warming over the whole hindcast period as well. So we have some encouraging skill in the first month and potentially into the second month for some seasons. And the idea is to understand how that propagates into the hydrological forecast, which I'll show in the next slide. I just wanted to also show the comparison across the different models. So one key thing that we did look was these 5 different models. And the idea here was to try to understand which models perform the best and in which seasons, which regions, and if there was potential to actually combine these different models based on their skill into a multi-model ensemble. So here, these maps here show a kind of normalized score, in fact, a weighting that we've been using to weight the different models based on their skill. So if the color is more red, then we give higher weight to the model. And if it's more darker blue, then we give lower weight to the model. So it's less skillful in that particular location. And you can see these lighter kind of blue colors here indicate that in the wetter southern part of the basin, it's the ECMWF model and the UK Met model that will be given the higher weight compared with the other models. And in the northern part of the basin, you can actually see that some of the models do quite poorly relative to some of the other models like ECMWF, for example. So in those places, a lot of the weight would be given to one particular model. Down in the southern part, there's a bit of a more even distribution with a bit more weight on these 2 models. So we've done some testing to see how that improves things, and it does a little bit. So we're still working on that. So the summary is to try to use multiple models where possible to improve the precipitation forecast at least. As I said, we use these forecasts and we use those to drive our hydrological models. And I'll just show you a couple of examples of the forecast evaluations for soil moisture, which is in this figure, and then for stream flow in the next figure. So again, this is spatial maps, and I'm showing just for the first 3 months lead here. So this is the first month, first lead 1 month of the forecast over the whole hindcast period. And again, it's in terms of correlation. And you can see some significant correlation. This is in terms of anomalies as well. So you can see some significant skill up to about 0.7, 0.8 across much of the basin. Of course, this decreases as we go out to further lead times, but we still maintain some skill in some areas that is significant as well. And this is a summary over one of the sub-basins here, showing the skill of the hydrological model forced by the ECMWF precipitation forecast and compared with ESP. So if you're not familiar, ESP is basically a climatological forecast. So we are improving on a baseline forecast with our approach here. And similarly, here's the results for stream flow. So we're actually predicting stream flow over about 70,000 river reaches, so very high resolution. And again, this is showing the skill of the forecast driven by the ECMWF precipitation forecast over these reaches in comparison with a historic simulation that's forced by the MS-WET observational data. And if you focus on the kind of bluer purple colors, you can see where there is considerable skill. And obviously this becomes even better for some of the larger river reaches, the larger upstream areas. So the Nile River itself, you can see that there is good persistence in the skill, maintaining to about 0.7, 0.8 in many parts of the basin, especially for these larger rivers. Obviously, there are places where the skill is very low. That's a function of the precipitation, but also the size of the basins as well. So that persistence in the initial conditions from the forecast is really important when it comes to thinking about the skill in the hydrological variables. Very much true for soil moisture, and even more so for the stream flow. Similar to the previous talk, there is also a web interface for this, and this is just a screenshot showing the conditions that were updated last month. So this is for February. We have an update for this month as well. And again, the interface provides access to the information in many different ways, including spatial data, time series as well. And there are various kinds of alerts and triggers as well that tell you quite quickly how conditions are changing. So whether drought is increasing in certain parts of the basin and so on. And then there's much more detailed analysis at the sub-basin level in terms of the forecast, all the monitoring and so on. And again, there is a report in a similar way to the previous talk that summarizes the current forecast and monitoring, and that's been delivered to stakeholders around the region as well. So in conclusion, just a few recommendations. So as always, observational data is key, in any endeavor like this. So having more data available is essential to improving the historic observational data, the gridded data, and validating that, but also to test out the forecast, the skill of the forecast as well, especially for the stream flow. The second recommendation is really trying to tie the drought forecasts and forecasts in general to actions and decisions. So it's all very well providing this information and doing careful evaluations, but these really need to be tied to the key actions and decisions that are happening in the kind of hydrological and agricultural sector in the basin. And this relates to the last point, is that dialogue is required with stakeholders on how those forecasts can be integrated into decision making, and how they can be more beneficial to those stakeholders. Okay, I'll stop there. I see, Motadir, you've appeared, so that's probably my time up as well. Thanks very much for listening.
Thank you very much for this excellent presentation about the drought forecasting activities at the Eastern Nile. And you showed us like this comparison of different multimodal based, and also the skills of based on their skills also this high resolution of flows and their skills, and the different kind of useful information. And also thank you for sharing like the web page or the website for our participants, so they can manipulate and generate different kind of information from that web page. Thank you very much, Justin. Please kindly stay with us. You will receive some questions by the end of this session. Thank you. Now we will go to our next presenter, Dr. Anwar. His presentation about meteorological and hydrological drought monitoring in the Eastern Nile River Basin. Dr. Anwar, please kindly first introduce yourself, and the floor is yours. You are welcome. Thank you.
Okay, thank you so much. My name is Anwar. I'm from Bahar Dar University. I was working for the last 10 or 12 years in meteorological and hydrological studies. Okay, okay, let me share my screen. Okay, is that working?
Yes, thank you. Thank you very much.
Okay. Thank you, Mudathir, and good morning for everyone. My topic is entitled in meteorological and hydrological drought monitoring in the Eastern Nile Basin. We did this work during the 3 months internship program of the Eastern Nile Technical and Regional Office, INTRO. I am from Ethiopia, and Milena from South Sudan, and Mubarak from Sudan. When we come to the introduction part, you know that drought is one of the natural disaster experienced in the Eastern Africa and also in the Eastern Nile countries like Egypt, Sudan, and South Sudan, Ethiopia. For example, we can see that in Ethiopia, droughts of the 1973-74, the 1983-84, the 1994-95, 2003, 2014 and 15 were reported as the major drought years. When we come to in Sudan and South Sudan, the two widespread droughts were occurred in between 1973 and 1980 and 1984. When we come to Egypt, in the last 30 years, 10 drought events were marked as a water flow deficit. like starting from 1972 to 2010. Especially in this country, rainfall variability in Ethiopian highlands and also in Lake Victoria caused significant interannual and interdecadal variability in the Nile flows. However, less progress has been made in monitoring and forecasting water deficits like drought. So the main objective of this work was to monitor the meteorological and hydrological drought in the Eastern Nile Basin. You know, I will not go in detail about the Eastern Nile Basin. You know about it more than me. It constitutes over 60% of the area of the Nile River Basin, and it contributes over 86% of the average annual flow of the Nile River. It has 4 sub-basins, the Takaziat Bara, the Blue Nile, the Baro Akobo Sobat, and the main Nile. When we come to the data set, what we have used during our work, we have used 46 meteorological stations in the Eastern Nile basin having 30 years data, starting from 1971 to 2006. The length of the data is different from one station to the other. And we have got this information or this data from meteorological agencies of the Eastern Nile countries and also from the intro database. We have used also the satellite rainfall data. It is the CHIRIPS, the climate hazard groups infrared precipitation with stations. It is about 0.05 degree resolution. We have used the data in between 1981 to 2018. It is easily accessible from the FuseNet website. We have also used 26 stream flow gauging stations data on monthly basis starting from 1971 to 2002. When we come to the data analysis, we have used the standard precipitation index SCPI and also the standard stream flow index SSI. Sorry for the misspell. For the SCPI, we have used 2 tools for the spatial and the time series data. The GeoClim, which was developed with the FuseNet groups that used the CHIRIPS satellite rainfall, and also we have used the SCPI generator. It was developed by the University of Nebraska. It reads observed precipitation data. These tools can generate SCPI in different levels like SCPI 1, SCPI 3, 6, 9, and 12. For this study or for this work, we have used the SCPI 3 and SCPI 12. When we come to the SCSI or the standardized stream flow index, it is statistically similar to that of the SCPI, and we have used the time series data of gauging stations to calculate the standardized stream flow index (SSI). So you can see the table that shows the ranges of the values of SCPI and SSI in the drought category. When we come to the key findings, we have produced multiple maps and graphs that indicates the drought, the extreme drought periods of the Eastern Nile countries in the Eastern Nile Basin. So for this, for the sake of time, I will show you some graphs and maps only. When we come to the SCPI from the historical rainfall in Ethiopia, there was a recurrent drought signal in every 10 years, which are the 1974, the 1984, the 1985, 2004, and 2015. When we come to the South Sudan, we can catch that there was drought in between 1976 and 1978 and 1982. 1982 and between 1982 and 1989, and also in 1904, 07, 09, 10. It is on the Malakal station. When we come to the South Sudan, the above was for the South Sudan. For the Khartoum station, we have both those periods of droughts. SCPI in Egypt, it is more likely there is no meteorological drought in Egypt. You can see that we can see some drought signals on in 1990s and 2000 because of that most of the upstream areas is suffering with or experiencing the meteorological drought. Okay, we can see that the SCPI from the satellite rainfall for the SCPI 12, you can see that the 1984, 1994, 2004, and 2005, there is a 10 years recurrent drought in the Eastern Nile Basin. This is for the 1984. This is for the This is the very severe drought in the history of the Eastern Nile Basin. And also this is for the 1984, this is for the 2004, and this is for the 2012. You can consider this 2012 as a neutral year. You can see that there is there is no drought in the basin. This is for the 2015. When we come to the some maps of the SPI3, you can see that the 1984 is still the most drought year in the Eastern Nile Basin. And also we can see that the 2004 and the 2015. In 1984, the annual drought was severe than the seasonal drought. The seasonal drought means the annual drought calculated with the SCPI 12 was very severe than that of the seasonal drought. Means that it is a prolonged type of drought in the 1984. When we come to the standardized stream flow index, SSI 12, most of the Eastern Nile Basin experienced two main periods of drought. It is between 1972, 1974, and 1982 and 1988. You can see that the Tana inflow, the Tana inflow in the Lake Tana Basin, and also the Blue Nile at Khartoum, and also the upstream Aswan inflow, Okay, from these results, we can conclude that in monitoring meteorological drought, satellite products like CHRIPS are very important, and they are the data is very trustable. If we do something like bias correction, it used like as an input for especially for hydrological models, because we have limited number of gauging stations. The low stream flow volume from the Blue Nile was a direct reflection of the low rainfall received in the Ethiopian highlands. This in turn impacts the storage capacity of the dams in the basin. As a conclusion, we had figured out these conclusions during that study in 2018, before 2 or 3 years. Increasing the number of weather stations is useful for the future drought monitoring studies, because we have used only 46 stations for the whole Nile Basin, and we have tried to interpolate these stations as SPI data, but it didn't represent the whole Nile because of the sparse distribution of the station. The other meteorological, hydrological, and agricultural drought indices need to be considered in drought monitoring. I know that the intro and also the main Nile, the NBI is working on the drought forecasting and monitoring things. That progress is very nice and it should be strengthened. Drought forecasting and drought risk assessment, especially the drought risk assessment, are very important issues that could be addressed in the Eastern Nile Basin. Thank you for your attention.
Thank you. Thank you very much for this nice and excellent presentation about meteorological and hydrological drought monitoring in the Eastern Nile. And you showed us like different analysis for this SPI over different stations, and also the analysis also for the same thing over the entire Eastern Nile. Thank you very much. Please kindly stay with us. You will receive some question by the end of this session. So before we go to our next speaker, I would like kindly to remind our participant to type your name, affiliation, and country of residence in the chat room so that other participants can know who's present. And for our speakers, please kindly mute your mic and turn off your camera except when you're speaking. And for our participant and also for our speakers, you can also use the chat room to share and exchange ideas. And for our participant, please, you can post your questions in the Q&A feature. This will be responded to by the resource persons. Also for our participant, when we open the question part, you can also raise your hand and we will give you a chance to ask your question directly to our panelists. Thank you. Okay, now let us go to our third presentation. Okay, our third presentation, it's by Maximilian. And the title of this presentation is Spatially Transferable Drought Hazard and Drought Risk Modeling Approach Based on Remote Sensing Data. Please kindly, Maximilian, introduce yourself first, and the floor is yours. You are welcome.
Good morning, everybody. My name is Max. I'm a PhD student from Munich, and I'm working at the Remote Sensing Solutions GmbH. And today I will tell you about a spatially transferable drought model based on remote sensing data. The aim of our study was to close the gap between global drought models and sub-regional drought models, where global drought models cannot capture regional drought effects, and sub-regional drought models are spatially explicit, but mostly not spatially transferable due to the availability of global datasets, for example. Our drought modeling framework captures drought hazard, vulnerability, and risk for crop and rangeland. And rangeland, in this case, is derived through grassland and shrubland. I will quickly go through the methods here. Here you can see our drought modeling framework. On the right side, you will see the drought hazard analysis, which is the bigger part and more important part. And then on the lower left side, you see also the vulnerability and risk analysis. So in a first step, we use land use classification to aggregate the land use classification to rangeland and cropland. Then in the next steps, we calculate our variables we use in the model. The first one is derived from CHIRP's precipitation data, where we calculate 3-monthly SPI. And then we also use different indices from MODIS data, where we calculate index anomalies, and we use the NDVI, normalized difference vegetation index, the NDII, normalized difference infrared index, and then also the albedo and the surface temperature. And then we calculate index anomalies, monthly index anomalies, and for the whole land cover. And in the next step, we train the model by gaining training data through yield data from the FAO. The FAO provides yearly yield data throughout the whole country. And we use this yield data and uses segmented regression, and then derive non-drought and drought years throughout the residual analysis. And then we assume that in a non-drought year, we don't have any pixels in drought status. So we use that as training data for no drought. And in a drought year, we would assume that every pixel in this country would be in drought status. So that would be the training data. We know that it's not the reality that every pixel is in no drought or drought status, but the model is quite robust, and we're only looking at quite big, large-scale droughts in the agriculture. So since using only croplands and rangelands, that proved to work quite well. Then we use a logistic regression model to calculate drought probability, which is also equal to drought hazard. And then in the next step, we also try to assess drought vulnerability. And since we're aiming for a spatially transferable model, we only use data sets that are globally transferable. So we only did the drought vulnerability and risk in a very exemplary manner because it's way more complex than on this slide shown. So we use, for example, farming animal density, population density, irrigation, so rain-fed croplands and irrigated croplands, and the GDP to produce drought vulnerability, and then combine vulnerability and hazard to produce drought risk. To evaluate our model results, we used the United States Drought Monitor in the USA. So we set up the model in the USA since they already have a very good tool for drought monitoring to verify our model results. We used the Global Drought Observatory, FuseNet data in Southern Africa, food security outcomes, but also a newspaper article and drought reports to verify regional droughts. And then also in Southern Africa and Zimbabwe, we used data on the El Nino event from 2015 to 2016, because there are known teleconnections, which means that during an El Nino event, we have hot and dry conditions between December and February in southeastern part of Africa, and we tried to see that in our model results as well. So on this slide, you can see the results from the drought hazard model for the US. So on the left side, 2012, you will see a year where we had a quite large drought. And then in 2016, you can see a year where we had a smaller drought. So the colors range from green to red, where red means high drought probability and green means low drought probability. It ranges from 0 to 1. And then you can see the dotted areas which indicate drought declared by the US Drought Monitor. And as you can see here, the US drought monitor matches quite well with our drought hazard model. So even in the year where we don't have a large-scale drought, as you can see in June 2016, for example, in the middle part, you can see that the patterns match quite well. After we got this good results in the US, we tried to transfer the drought model to Southern Africa and Zimbabwe. Here it was way more complex to verify our model results. That's why we used different approaches. We used, for example, drought reports and newspaper articles to verify our model, but also the Global Drought Observatory that you can see here below. This is an example for February in 2016. And as you can see, the spatial resolution of the Global Drought Observatory is too low to verify our model in a quantitative manner. So we only used qualitative verification. But as you can see, over the whole country of Zimbabwe in this month, there was a widespread drought with very dry conditions. And also the FuseNet data verifies our model in this case. On this slide, you can see the combination of drought hazard, vulnerability, and drought risk for two seasons, 2013-14 and 2015-16. We only demonstrated this for the growing season for cropland. And as you can see on the top right in the drought year, the teleconnections from the El Nino event are quite good shown because we have high drought hazard in the northeastern part of South Africa and the whole country of Zimbabwe, but lower drought probability in the southwestern part of South Africa. In the middle, you can see our drought vulnerability combined by the factors I explained before. And then down below, you can see the aggregated drought risk map on the left for a non-drought year where we don't have any large-scale droughts, and then for a drought year where we have large-scale droughts over both countries. So due to the short manner of this presentation, I wasn't able to set up the drought model over the Nile Basin. But during another project where we analyzed transhumance in Chad and Central African Republic, we also used the drought model. And here you can see accumulated maps for the whole growing season for the years from 2011 to 2018. So we transferred the model also to Chad. We also tested the model in Germany, for example, and we're still working on different application methods. So we're also testing the model in Brazil and got quite good results. We're working together with another team that's working on groundwater data from the GRACE tool, and we're working together with some stakeholders in order to predict yield in agriculture with our drought model combined with the groundwater measurements from GRACE. And yeah, so in the future, we try to transfer the model to different regions. We already know that it's working quite good in, for example, semi-arid regions and arid regions, but also now in Brazil. So we try to do more feasibility studies, and then maybe also try to work with that model in the Nile Basin, and then also try different applications, for example, as 2 to 3 monthly yield forecasting, as we try to do it in Brazil right now. Thank you for your attention.
Thank you. Thank you very much for this nice and excellent presentation, Maximilian, about especially transferable drought hazard and drought risk modeling approach based on remote sensing. And you gave us like a very nice result during, along different regions here in Africa, like in Southern Africa, in Zimbabwe, in Chad, and also in Missouri. Thank you very much also for sharing like the workflow of the drought hazard vulnerability. Very nice presentation. Please kindly stay with us. You will have some question later, please. Now I would like to ask Kevin. Kevin, are you there? Okay.
I am here, yes.
Okay, very good. So before I come to you, I just would like to remind our participant that please type your name, affiliation, and country of residence in the chat room so that other participants can know who's present. And also you can exchange your ideas also in the chat room. You can share your ideas. You can post questions in Q&A. And after the reflection from Dr. Kevin, you can also raise your hand and you can ask your question directly to our panelists and to our speakers. Now I would like to give Dr. Kevin from University of Oxford to reflect on today's session. Thank you. Please kindly introduce yourself and the floor is yours. Thank you.
Thank you very much, Dr. Mutada. My name is Kevin Wheeler. I'm a researcher from the University of Oxford and have been working on the Nile for the last decade or so. This is a wonderful opportunity. I always love, this is my third Nile Basin Development Forum that I've participated in. And I think they continue to get better. And it's a challenge this year, obviously, to try online. So I didn't prepare a presentation, but simply watched the presentations that were given, and so I could think about them a little bit. I think some of the first things that come to mind is these are obviously very appropriately focused on the scientific side. Droughts are not political. The amount of water that's available in the past will be available in the future. That's not a political question. So this forum is an excellent opportunity to highlight the science, really, of trying to separate the science from the policy. And we're really focused on the science in this, how much water is available. And of course, to do that, as the speakers pointed out, a strong need for data, for the verification, validation of the methods used, the need for data. The technologies are improving constantly to be able to forecast, but that of course relies on having a good basis of information to do this from. Access to historical information, actual flow data to help develop, verify, validate, improve these methods that are being used in these tools, and then access to real-time data to validate if the tools are working properly, if the forecasts are actually giving us some good numbers. And these forecasts, these products will continue to be improved with improved technology, improved satellite information, et cetera. And I think an important thing to think about is to make sure that we remember that pretty pictures don't solve the problems. Data solves the problems. We could develop really nice maps, but it's important at the basis of all of these tools to make sure that the information that comes out of the tools are easy for people to use. So whether that's the basic text files or spreadsheets is the first way to disseminate this information, and then having maps and having visualizations on top of it to help the public understand more what the distributions are. So I think it's important to not substitute the basics for the complexity. So often I say things should be as simple as they need to be, but no simpler as they have to be. Again, maps and analytical tools are very nice, but they're not secondary to the pure functionality of being able to provide this information, so decision makers can plan on the operation of the reservoirs or preparation for severe impacts on humans and on economies and on societies. I think Dr. Anwar had a very important point about the increasing need for weather stations. That the fact that there's more satellites in the air doesn't say you need less weather stations, but you still need them to be able to validate that information. And it of course takes funding and money and commitments by the governments to improve the number of weather stations. And so, as I mentioned yesterday, the goal of the forecast is not necessarily to generate reports or generate studies, but to be able to provide a product, to provide a data product that others can use, and making that accessible for people is the number one goal. So after the data collection, data dissemination are the first pieces, and then the processing and the analysis are the second pieces to that. And as I was saying, transparency is the key to success. So with that, I would just wrap up by saying the goal of the forecasting is to provide the best estimates of past and future flows, regardless of who might use that water. How much water exists is not a political question. That's a humanity question. That's an environmental question. And the goal of the science, as us as scientists and engineers, is really to try to figure out and try to say how much water is available. Now, there's been a time on the Nile and in river basins throughout the world where it was advantageous to not show how much water was available. But with the increasing satellite, it's actually becoming advantageous to show how much water is available to be able to demonstrate the best way to manage that water into the future. So we're shifting from a paradigm of information secrecy to a paradigm of information transparency by necessity. It's going to happen anyway. And these tools are helping that process along. And the question is, how good can these tools be to move into that new paradigm of transparency? Those who produce the best forecasts will have the most legitimacy within the discourse. So I'll leave it at that. And again, it's a separation of the science and the policy. And purely in this conversation, we're focused on the science and we're focused on the development of the tools to give us the best information. So I'll leave it at that.
Thank you very much, Dr. Kevin, for this excellent insight and excellent reflection. Thank you very much appreciated. I'm happy now, Robert, the expert from WMO, he's on board now. Maybe I will give you another chance, Dr. Kevin, to reflect again after his presentation. Robert, are you there?
Yes, I'm here.
Excellent. Thank you very much. So now we will have our final presentation by Robert, the expert from WMO. Thank you very much. Thank you. Okay. Please kindly introduce yourself, and the floor is yours.
Thank you, and my apologies. I have this issue with East Africa where I think it's the same time zone as Geneva, Switzerland. And you are always an hour ahead of me, so my sincere apologies, and it's a pleasure to be here.
No problem. You're welcome. You're welcome.
My name is Robert Stefanski. I work for the World Meteorological Organization. And of interest to our participants, I help lead the Integrated Drought Management Program, which is organized by the WMO and the Global Water Partnership. But as important, we have over 35 partners that help deal with issues related to drought, early warning, vulnerability assessments, and drought mitigation and response. So can you see my screen?
Yes, you can only put it in slideshow mode, please. Yes.
There we go.
Yes. Thank you.
So yes, and I'll be fairly quick. Again, I appreciate your time, and so let's get started. So within the drought program, again, we have 3 pillars, and I'm only going to focus on the first one, which is drought monitoring and early warning systems. And I think some of your other distinguished colleagues have probably talked about this as well. But again, why monitor drought? Drought is a normal part of the climatic cycle. Of course, we all know the impacts are significant and widespread, and also drought is expensive. And again, as your colleagues will also know, just about every climate regime in the world can be affected by drought. And just to be clear, so we're talking the same language, again, especially from the sense of, let's say, meteorology and climatology, and there's a lot of discussion on this. Again, we consider drought as a temporary, basically it's an event that it's caused by a lack of rainfall, a deficit of rainfall, and at some point can return, if you will, to normal or to a more normal condition. I want to stress that we're talking about the physical, let's say, rainfall regime. And so, but the impacts of a drought can last far longer than the actual event. And we're working on that with many other organizations, and especially the United Nations Framework Convention on Climate Change, to try to delineate the drought hazard. So the importance of a drought monitoring system, again, allows for early drought detection. It improves response. And again, I think some of the other speakers have probably talked about this. A drought is a slow onset phenomenon, which means unlike a hurricane or a severe thunderstorm, where it can happen fairly quickly or within a day or so, a drought condition develops over time. It could be weeks, it could be months, and then the impacts can be quite severe. Again, I think for our colleagues in Africa, just the situation that occurred in Cape Town, South Africa, a few years ago is a good example of that. So the monitoring system also would trigger actions within a drought plan, and this is the foundation of any drought plan. So again, the components of an early warning and information system is we're considering monitoring and forecasting. So again, you need to monitor the situation, and this can be done by various indices, and I'll show that. Also, these are tools for decision makers. Again, looking at the condition in Cape Town, they were looking at the various indices, and these can range from, just simple rainfall to the situation in the reservoirs, et cetera. It's also needed for or useful for drought risk assessment and planning and education and awareness. But just quickly, some indices and data issues. You can use a single index or parameter, multiple index, or composite index. And the importance of these indices are to simplify complex relationships. And I think something that's not talked too much, but this also provides a good communication tool for diverse audiences. They can provide a quantitative assessment of this anomalous climatic conditions, i.e. the intensity, duration, and the spatial extent. It also can provide a historical reference, the probability of reoccurrence. Within the Integrated Drought Management Program, we have a handbook of about over 50 drought indicators and indices. Again, this is a starting point. What we try to do is not be prescriptive. Again, drought indices is a complex issue. Various countries and regions will look at different indices. Within a country, you'll look at different impact sectors, i.e. agriculture, urban, ecology, ecosystems. So what we try to do is provide an overview of each indice and indicator, providing any scientific material, even computer source code, and what it's used for. So again, to select these indicators, you need to have the appropriate, it's a timely detection of the drought to trigger appropriate communication and coordination. needs to be sensitive to the climate, needs to reflect the impacts occurring on the ground, excuse me. Again, it also triggers actions, and is it easy to use? Within the context of WMO, as some of you might be aware, we represent about over 195 countries, and this is primarily the national weather services and hydrological services of each country. And we've actually have recommended to use the standardized precipitation index because it's statistically significant and also is easy to use. And so this is something to be aware of. You can use a very complex indicator, but if you cannot communicate what this indicator is doing to a prime minister, to a minister of environment, utility of that indicator is fairly low. Just some data issues. We need long-term accurate data, and I know the previous speaker was talking about that as well, so that's very important. However, there's other data that could be used. Potential evapotranspiration, basically how much it's evaporated. What kind of, especially for agriculture, do you have conditions on crops? Do you also have soil moisture information, reservoir information, etc.? More and more, of course, we're using global data sets. And one center that we're using from that's hosted by the German Weather Service, this is Global Precipitation Climatology Center data. And there's many others as well. One important thing, and WMO and other partners also liaise with the United Nations Convention to Combat Desertification, and one of our strong recommendations to the global drought community is, while we do need more weather and climate data, the vulnerability and impact data are very limited across the countries and across the period of record. These are just some examples of actually indices in Africa. This is from the center in Niger, Niamey, Niger, the African Center for Meteorological Applications for Development, looking at a continent-wide, I think this is this percent of normal. This is from Nigeria, just again looking at the number of rain days. These all could be considered indicators. Hydrological flow, this is for the Niger River in West Africa. Again, it can be quite important information. And also looking at crop stress, this is in Cote d'Ivoire. Also the satellite information from Burkina Faso, looking at this normalized difference of vegetation index going back in April. Again, looking at the satellite information. We talked about forecasts, and this is a subject that WMO is working very hard on. I don't want to go into too much detail, but within the WMO network of countries, we also have something we call regional climate centers, and they also provide climate forecasts for the next 3 months. And this is an example from West Africa, looking at the percent of basically above normal, near normal, or near to below average. One thing, so this is one thing that we integrated into if you have a drought monitor, you can then combine it with the forecast. And that will give you especially going into a rainy season, that'd be quite helpful. One thing we're trying to do, we have about 20 of these centers, more or less 15 to 20 of these centers across the world. And we're trying to really increase the objectivity. If I could say, making sure that these are reproducible and that we can also provide more detailed information, for example, on the start of the rainy season, the end of the rainy season. Are there going to be any periods of dry weather during the rainy season? Again, those are all useful for drought impacts and early warning. So again, looking at this pillar on early warning and monitoring systems, you're going to have integrated monitoring of key indicators. These are used to trigger actions in drought plans. You need reliable seasonal forecasts. And also that you need good communication and delivery of this information. Again, these are the types, just a quick overview of the indicators and indices. and also the ministries and organizations and agencies that would provide this. Of course, this is a group effort. One thing we stress in the global drought community, again, we have partners and colleagues from the Food and Agriculture Organization. I mentioned UNCCD, we have UNESCO, WMO, we have many other partners. So this should be replicated in the countries. So we really advocate, you should be talking within a country, among yourselves, across the ministries, across the agencies. Again, the ultimate goal here is providing the best information for your citizens and decision makers on drought issues. And so I'm going to leave it at that. We have the IDMP Help Desk. It's a website with many kinds of information. And I just want to give you a very short overview of drought early warning and monitoring systems. So I'm available for any questions or discussions. Thank you.
Thank you. Thank you very much, Robert, for this excellent presentation. And thank you for sharing with us the WMO experience in the drought monitoring and early warning, and also the WMO products and how to select like drought indices and the issues with data. And also thank you for sharing like some interesting result from different countries in Africa. Please stay with us. You will receive some questions. I would like to go now back again to Dr. Kevin from University of Oxford. If you would like to give like some further reflection. Thank you very much. The floor is yours, Kevin.
Okay, that was very good to see, and I'm always trying to figure out how WMO fits within obviously the global, but as well as the local context. And I think something that Dr. Stefanski said at the end was important. The interaction between the global assessments that they're able to do, as well as the local assessments. This should be a two-way stream of communication. Obviously, the information from the ground of what the emerging potential for droughts are, that's going to come from the local gauges and from the local both precipitation stream flow gauges. So that information is critical to pass to the analysts on whatever institutions they're with, whether that be WMO, or whether that be with an NBI, and then that information gets transferred across the different countries again, so people have a common understanding of what the potential severity of an upcoming drought would be. So I think what we're seeing is there's a lot of different products that are available, that either in the government realm or the multinational realm, as well as the research realm. And I think this is where the challenges are going to lie of where what tools the countries need and want to use, and what arrangements do they develop to share the information to improve these tools and to utilize these tools. And I imagine it would be on a contractual basis, sort of agreements between both between the countries and these organizations, as well as agreements between the countries to be able to coordinate their drought management strategies. And these, of course, have very real implications that the countries have similar views on what droughts are going to look like in the forthcoming months, particularly as we live in a more integrated world where we depend on each other for our management of resources. So I think some very good things I would be interested in watching that talk is looking at other river basins around the world. How do shared droughts or how do drought information and management get utilized between other transnational, transboundary river basins? in a talk or a session we'll have next week on coordinated operations of reservoirs. One of the sessions on March 31st will be with we'll have examples from the Colorado River, another river I've worked on, where U.S. and Mexico worked together on figuring out how to coordinate the management of droughts, and of course having a common understanding of what are the indicators of a drought. How do we determine what a drought is? Was a very critical part of coming to an agreement between the countries. So yeah, this is where the science starts to meet the policy interface when you talk about coming to agreements between the countries. But still, at the very base of it is, do we have an agreement on what a drought is, and how soon can we predict that, and what the severity of that event may be. So I would certainly encourage continued interaction from WMO and as these drought monitoring forecast tools are rolled out from NBI, to make sure that information is widely used and widely accessible and critiqued. In science, I've realized it's important to receive the critical feedback to improve. That's the only way we improve these forecasts, is to constantly have them put out there for review, for critique, for people to say this is right, this is wrong. We improve it and put it back out there again for the next cycle. So that's all I have from that right now. But thank you very much for the opportunity.
Thank you very much, Dr. Kevin, for this excellent reflection, and also thank you also for stressing that on focusing on science to inform policies. This is a very important message. Thank you very much. Thank you. Now I would like to go to our panelists. There are some few questions for them, and I'm encouraging also our participant, if you have any question, you can write it on the chat, or you can write it in the Q&A, or you can even raise your hands. So I would like to start with Justin from Princeton Climate Analytics. There is one question here for you. You have excellent products and very nice products and very nice web page, which can give different kind of very useful information for the Eastern Nile related to the drought monitoring and forecasting. But we would like to know, what are the challenges in communicating these nice products and this nice information? And how did you manage to overcome this with Intro? Thank you.
Yeah, thanks for the question. Yeah, and it's a very important question. I think that's kind of been highlighted by other speakers as well, as how you actually use this information and communicate it as well. And I think it's important, it was touched on by other people, about having a variety of ways of providing that information, whether it's for the general public in terms of maps, visual aids, or whether it's the data itself. And that could be the full data set, including all the historic data with all its complexities, but also simplified tools and data sets, simple text data sets that can be imported into spreadsheets. So I think it's really important to have that variety of information, from the full technical right through to the visual aids, and that helps to engage with a whole range of stakeholders. And having this information up to date and operationalized is really important. And also, I think it was mentioned by a few people as well, is having that self-critical element to it as well, where you're always thinking as a data provider or a product provider, you're always thinking about the quality of the information that you're providing. Again, that links to the idea about having good on-the-ground data to verify. So again, it's really a combination of things that's required here to overcome these challenges around communication. One challenge we did have is trying to integrate the system into what Entro was doing already, which we tried to do, and we're getting there as well. So having this ownership of the systems essentially is crucial. And we all know there's huge challenges in trying to download all this information in an operational sense and have this available all the time as well. So a range of challenges and a range of solutions as well, but essentially providing a wide range of information, I think, is important to a wide range of stakeholders and potential users.
Thank you. Thank you very much. Thank you, Justin, from Princeton Climate Analytics. Thank you. There is one question also for Dr. Anwar related to the nice analysis you made about the SPI. So in Sudan and Ethiopia, of course, they depend a lot on rain-fed agriculture, but you also did like some nice analysis also for Egypt, also by using this SPI, this standard precipitation index. Do you think it is like a good approach also to use this SPI for Egypt, knowing that in general it has like a very little rainfall? Thank you.
Thank you. Yes, you are right. It is to show the results, or to show the meteorological drought for because we should fairly compare the meteorological drought from the 3 countries and also the hydrological drought from the 3 countries. That is why I was displaying the results from Tanta station. You know that there is a little rainfall in Egypt, and we have not get any meaningful result on the SPI on Egypt. Mean that the drought in Egypt or the drought experienced in Egypt for the long period of time is hydrological drought rather than meteorological drought. Okay, thank you.
Thank you very much. Thank you for this nice answer, Dr. Anwar. Thank you. The next question, it is for Maximilian. Maximilian, are you there?
Yes, I'm here.
Okay, excellent, very nice. Okay, so your model generated a very nice result for different countries like in South Africa, Zimbabwe, Chad, I think Missouri also you showed us. But are all the steps automated, and is it easy to produce also results for countries, like countries in the Nile Basin? Is it easily you can generate like similar maps also for the Nile Basin, or it is time consuming if you want to replicate the same thing for the Nile Basin? Thank you.
So the transfer of the model is quite easy since everything is automated from data download to data processing, also the whole modeling framework. It's just kind of time consuming because it's a wide range of data you have to download, time series data from the year 2001 when MODIS first has the first data till today, and then also get the yield data and everything, because there's a kind of a different analysis behind that. We use the 5 main crop types in that specific country to determine agricultural drought defined by the yield. And the model needs to be set up regional. So you can't use the same model equation for another country, but the whole modeling framework is transferred and then set up newly with the new available data in that country, because the variable importance in the model changes from country to country. For example, the NDII index from MODIS is very important in the US, for example, since that reflects also irrigation. And then in Chad, for example, the SPI, the rainfall data, was way more important than the NDII, for example. So you have to regionally set up the model, but that it works quite fast in terms of working hours, but the processing needs some time.
Thank you. Thank you very much. We have a question here from Dr. Saleh. It is for all the speakers, but I will start with Robert from WMO to answer first. The question, you can read it in the Q&A, but I will read it for you. The question says, what are the strategies for making sure that national concerned agencies have picked up the drought indicators and took the necessary action plans to mitigate the expected hazard? So this is the question. Yeah.
Sure.
No, you can start with Robert first, please.
Thank you.
Thank you.
One thing that we advocate across all the partners on the drought community is developing a national drought plan or strategy. And again, just with the previous comments, this is where you really have to adapt the drought indicators to the situation. So again, the SPI may not be relevant for Egypt, but maybe a hydrological kind of index might be. So we advocate a national drought policy. And again, we mentioned these 3 pillars of drought monitoring, early warning, number 2, vulnerability impact assessment, and number 3, drought mitigation response and preparedness. They all lead to cumulate in a drought policy or plan. So again, we've done this in the past. You could have a stakeholder workshop. You bring all the people, all the stakeholders together. And so again, the country has to be internally organized on this. That's a challenge, I'll be quite honest. I come from the United States, and this is an issue across all countries, no matter if you have resources or not. And in fact, we find, again, we've been working on national drought policies with other partners. And it seems to me that the smaller countries maybe do a better job because they know everybody and they maybe get along better. And that's a general statement. But that's what to answer that question, that's the strategy. So you need to be organized. You need to talk to your colleagues. One of the big issues there, and I think you saw it when he talks about having picked up the drought indicators and necessary action plans. Again, a lot of the issues is what is the lead agency? And again, that has to be negotiated. But again, everybody makes a contribution. So if you're developing a drought plan and you have thresholds and indicators, you can use, something very simple like the SPI, or in the Nile Basin, river stream flow. You can then use other indicators for soil moisture, for other impacts. So all these indicators can be nested. But again, that has to be done through the national coordination. Again, understanding the Nile Basin, it's across countries. So again, you have to do that work across countries. But it is something that can be done. It's done in other regions. And I think people know, especially from the hydrology point of view, there's a lot of sensitive data there. When you talk about transboundary water flows, it's probably one of the most contentious issues. But again, I think through discussion, negotiation, and having a plan helps deal with that strategy. Over.
Thank you. Thank you very much, Robert. For Justin, would you like to add something maybe? Justin, are you there?
Yeah, sorry, having trouble with the buttons. Yeah, yeah, not much to add. Just to kind of echo what Bob had said there, that it's really important to have the national agencies coordinating and the cross countries as well. And a lot of this is about awareness raising as well, making sure that these tools and new products are provided and known about. And this is why these kind of events are really important as well. So getting as many people aware of the new technologies and how they might be used. And that's why it's important to have these kind of websites as well, to ensure people can access the information. It's not just a flow of data that's happening over the internet. It's actually a visual interactive set of tools that people can use themselves as well. So yes, agree with what's said by Bob, but just wanted to highlight that the awareness raising is really important across different types of stakeholders.
Thank you very much, Justin. Thank you very much. I think for our scientist, Maximilian and Dr. Anwar, maybe you are like more in science, not in like working on strategies and things related to like national agencies. So maybe it's enough like the answer we get from Robert and from Justin. Now we will move to the last part of this session. I would like to give the floor to Ammar Jabir, our rapporteur, during the 4 sessions under this climate for adaptation like theme. He was our rapporteur, and he was also at the end summarizing and also giving us some takeaway messages. So Ammar Jabir, please kindly introduce yourself first and give us like the final summary and takeaway messages.
Thank you, Dr. Mudathir. My name is Ammar Jabir. I am the Secretary General of the International Forum of Meteorological Societies, IFMS. I have the honor to rapporteur this webinar, and also I would like to thank the panelists. They provide more information and useful information. I would like to summarize this. First of all, climate drought is obvious, and its impact is seen over the Nile Basin. There is a variety of products that and tools that provided by NBI to support the decision maker and practitioners in the better management of water resources in the region. Development of drought forecast over the region and the challenges that it faces, like data availability, data assessment, accessibility, and also the main challenges is the data dissemination. Although there is interactive and web-based tool, but I think more mechanism for dissemination is required to enlarge the coverage, the dissemination coverage for the practitioners and decision makers in the region. Provision of meteorological, agriculture, and hydrological drought indicator and indices in the region is very important. And tailoring this product to the community needs is also important. There is not much effort exerted for drought monitoring and forecasting in the region. Therefore, more monitoring strategies and efforts should be exerted. Utilization of the satellite data is crucial for drought monitoring, and now we see in TRAPS data is used and also models for agriculture drought. So this is good and provide more data for developing these indicators. In certain countries like Sudan, South Sudan, and Ethiopia, the drought cycle are identified from the historical data. So it guides the forecast. stream flow of the Blue Nile is affected by the amount of rainfall. This is one result from the studies that conducted in Sudan, South Sudan, and Ethiopia. A more weather station is crucial for drought monitoring. Also, considering meteorological and agricultural drought should be used, or should be considered, and tailoring this product. Transfer of the model to arid and semi-arid region, like in the Nile Basin, is needed. WMO integration, integrated drought management program, is very promising, and it support many countries, including African countries, and also the provision of provision of handbook of drought indicator and indices is very useful, I think, for the practitioners here in Africa. It guide them to select and also adapt the climate drought indicators. Recommendation of the usage of drought indices, and also to communicate this drought to the decision maker is crucial. Data issues like accuracy, format, accessibility should be sorted out and solved. Weather forecast and climate prediction through the WMO regional center should be utilized to improve the drought monitoring and forecasting. I think that is all, and I will provide a very comprehensive report out of this webinar. Thank you very much.
Thank you very much, our rapporteur, Ammar, and thank you very much for this summary and also these takeaway messages. Allow me finally to thank all the panelists and the speakers for this session. I would like to thank Ammar Jabir, Azab Mersha. I would like to thank also Anwar, Kevin. I would like to thank Maximilian. I would like to thank Robert and Justin, and allow me also to thank the people behind the scene, Dr. Azza, Patrick, and Sued, who help us with IT things. Allow me also to thank the communication team. And finally, just I would like to quote one statement from Dr. Kevin. When he mentioned that this Nile Basin Development Forum, it's an excellent focusing science forum to inform policy, because at the end it's important we inform policy from these excellent results and excellent work. And I'm quoting also one of our previous speakers when he said that this climate change and this drought, it doesn't know boundaries. So let us continue cooperate together. Let us work together, and let us share the knowledge and information we have. Thank you all very much for attending this session. And I would like to remind you finally that we have more other interesting sessions, not under this theme. This is the final session in this theme, but we still have other sessions in the afternoon and for the coming 3 weeks. Thank you all very much. Thank you. Thank you.
Thank you. Bye-bye.
Bye-bye. Thank you.
Thank you. Bye-bye.
Bye-bye.
Bye.
Bye.
Thank you, colleagues.
Bye-bye.